Good morning, all. Shall we start the class? Is everything going fine? Shall we start the class? Am I audible? No. I hope I am audible. Let us start this session. In the today class, we are going to start. That is, we are going to revise one more beautiful chapter that is simply called magnetic coupled circuit. Of course, magnetically coupled circuit. First of all, just what is this magnetically coupled circuit? What are the things that you have to majorly cover? I will just recapture once. It is your responsibility to cover everything. In two-port network also, we have seen a variety of questions and variety of zones. But listen, in two-port, I have already clearly told you what are the things that you should keep it in your mind. We saw there are so many questions in the previous sessions, and we saw how the questions were asked, and I have proved also with the help of Thevenin's theorem and how we are normally calculating the parameters. And you must know how to bring one parameter from another parameter. That is very important. Suppose if Z parameter is given, then how will you bring the ABCD parameter? If ABCD parameter is given, then how to bring the Y parameter? So the conversion between one parameter to another parameter is very important. You must go ahead with this procedure. So I taught these things already in the lecture. So kindly go through it once and then try to solve very few problems related to that. That will be helpful for you. And apart from that, when two impedance parameters are connected in series, what will happen? When two admittance parameters are connected in parallel, what will happen? Like that, when the parameters are connected in series and parallel configuration, how do I calculate the equivalent value? That is one more important thing. So though they may not ask these type of question in the previous years, you can expect those type of questions in the upcoming exams. So it is very important to go through those points. Okay, fine. So let us start the next chapter. This is called magnetically coupled circuit. I hope you all have revised the fundamental basics in the magnetic coupled circuit. So let us directly start the problem because there are no big things to learn here. It is as usual, normal electrical circuits only. But what is the difference between magnetical and electrical? The difference is here we are going to see the magnetic flux linkage between the two coils. When we are having two coils, we must observe the flux linkage. Not only between two coils, it will be more than two coils also. I am just giving. See, when the moment we are injecting the current in the first coil, what will happen? Immediately, according to Weierstrass principle, flux will be started circulating in the first coil. So that flux will be started keep on revolving from north pole to south pole like this. So when the moment it is traveling and cut the secondary coil, one more inductive coil. Suppose in the vicinity of the first inductive coil, if you bring one more coil, what will happen? Now if you observe the diagram clearly, see that the magnetic flux lines offered by the first coil, it's keep on going and touching the secondary coil and crossing. So when the moment it is doing in this kind of mutual action, actually I am not passing any current through the secondary coil. I am simply passing the coil through the first coil. But the flux created by the first coil current will be linking, is trying to link with the secondary coil. When the moment it's trying to do this kind of action, what will happen? definitely this secondary coil will experience some force. See, someone is coming here suddenly and it is crossing them, he is pushing, he is keeping some force on the secondary coil. These flux lines will going to keep some force on the secondary coil. So definitely some magnetomotive force will appear inside the coil. So this is called mutual linking or mutual relation between the first coil and the secondary coil. Now if you observe carefully, suppose the first coil, how many lines it is producing? Line number 1, 2, 3, 4, 5, 6. So opposite sides also same. So totally 12 lines are going. Let us take, there are 12 flux lines. Total flux produced by the first coil when the moment we are passing the current. So it is producing 12 lines. Out of these 12 lines, now just let me know how many lines are crossing the secondary coil. Only two lines, see there, only the last two lines, this one and this one is touching the secondary coil. So they are called mutual flux. Mutual means they are having the mutual linking between the primary and the secondary. Now here, out of this total, if I will take 2, this is called coefficient of coupling. What do you mean by coefficient of coupling? Coefficient means it's a factor. What is the amount of flux that is linking with the secondary coil from the total flux offered by the primary coil? So we can define it in this way, that is 2 upon 12. So this is the amount of flux that is linked with the secondary coil out of total flux. Out of total flux means 12. So it will be 1 by 6. In percentage, you can multiply it by 100. If you want to write it in percentage, simply multiply it by 100. Nothing will happen. Are you getting me? It will be 50 by 3. Or I can say, what is the percentage? It will be 1 6.666 percentage. I hope I am correct approximately, right? So this is the coefficient of coupling in percentage. That is how flux are linking with the secondary point. I hope you would have understood. Now, in the same way, if you observe, now the second question is coming fall in place. What is the second question? Sir, you have passed the coil only through the primary coil, right? If I will done the same thing with the secondary coil in according to our examination point of view from the basic network theory, they won't give two different number of coils. What they will do is, in I'm talking about electric circuits, in transformer we have some different number of turns. We will see those kind of things in transformer. So in electrical network, what they will do is, in circuit theory, they will give same number of turns. Now, so far we have been discussed with the first circuit. Suppose if we will do the same thing with the second circuit, what will happen? Like if I will inject the current through the secondary coil and if I am removing the current from the primary coil, what changes might have happened? Nothing, but just observe the direction of the current. Initially, I was passing the current from C. This is going from left to right. Don't forget this. This current is going from left to right. Now, we have observed the changes. Now, if I will, let us see. See, when the moment I was injecting the current, first what I have done is I have injected the current from left side to right side. Current was going from left side to right side. That is the first case. So we have understand. Now in the same passion, what I am going to do is, let me take this secondary coil. I am injecting the current in the same passion. Now what will happen when the moment you are trying to inject the current through the coil according to our state principle, once again it will start producing magnetic flux lines. So it will started producing the magnetic flux lines. And remember one more thing, just now I told you usually they will keep same number of coil here. So I am keeping 3, 4, it will be 4. Then we have started that last two lines only, in the last case also started linking with the adjacent coil. Just for an example I am taking. Okay, so let me take this line little here. Okay, so totally just assume that two lines are crossing here. So totally we have injected last case I think 4 lines. I haven't observed the opposite side, only I have counted 2. But anyway, it doesn't matter, just to understand the concept. Just see how many number of lines are linking with the this coil, that is the primary coil, when we are injecting the current through the secondary coil. So this case will be remained same. Actually what will happen when I was injecting the current through the first coil, let us take two lines were injected, two lines were creating the effect or influencing the secondary coil. Similarly, when you are injecting the current through the secondary coil, same number of flux lines will be creating the influence in the first coil. So the coefficient of coupling will be remain same in both of these cases. And the next thing is, basically what will happen is, we might have observed there will be some changes. We know basically when the moment we are passing the current through the single coil, if I will pass the current through this coil, what will happen? Flux will started emanating from north pole and terminating into south pole. So let me call this is north pole and this is south pole. Okay, sir, fine. There will be no issues. So it is started traveling like this. So definitely what will happen because of this flux, some self-inductance will be produced. So we can see. So here the self-inductance offered by the first coil is we are calling it as L1. Let me call like this. Similarly, if I will pass the current through the secondary coil alone, same thing will happen. Flux will be started flowing from north side to south pole, north pole to south pole. So I can call the self-inductance value as L2. So when I am bringing the first coil into the second coil vicinity, or if I will bring the second coil to the first coil vicinity, what will happen? See, when the moment I am passing the current through the first coil, let us take only two imaginary lines are crossing the secondary coil. Because of that, one inductance will be produced that is called mutual inductance. This is the mutual linking. This inductance will be, see, actually what will happen is when the moment you are injecting the current through the first coil, some of the flux lines produced by the first coil will go and link with the secondary coil. During that, some mutual inductance, some inductance will be developed in the secondary coil, but that inductance will be created with the help of the current flow through the first coil. In the same way, if you pass some current through this coil, it will produce some flux lines. That flux lines will go back and interlink with the secondary coil, primary coil. So I can say because of this current production in the secondary coil, some some inductance will be built here in the primary coil, that is called mutual inductance. So mutual inductance means basically it is the flux interlinking between the two coils, that is called mutual flux. In our electrical machines, we people are calling this mutual flux as what? Useful flux. We are calling this flux as useful flux. Because if you take, let us see, if you take the transformer, what will happen? In transformer, when the moment we are passing the current through the primary coil, because of that current flux line will come, that flux line will go on to cut the secondary coil. Yes or no? So when we are injecting the current through the one coil, because of that some flux line will be produced, that flux lines will going to create some influence in the another coil, that is called main field flux, or we are calling it as useful flux. So here our major concern, basically we are keeping our attention with only this useful flux. In the same way, if you inject the current in the secondary side of the transformer, there will be some flux will come that will go on to create some influence in the primary side. That is basically we will be calling it as armature reaction, but that armature reaction effect will be cancelled in transformer, because when transformer secondary will produce 4 lines, immediately extra 4 lines, immediately transformer primary also will create extra 4 line and it will cancel this effect. Oppose this opposition cause and opposition effect you might have gone through in transformer. Basically what will happen is when you are connecting variety of loads in the secondary side of the transformer, based on the nature of the load, different amount of flux lines will be created in the secondary side. That flux lines will be directly cancelled or destroyed by the primary flux. So that is some of the operation. Such that in resultant what will happen? Because of the load, there will be no any effect inside the transformer. Transformer will be trying to maintain the same flux at all time. If there will be any extra flux will be produced at the secondary side, immediately that will be killed by the extra flux created by the primary coil. Primary coil will intentionally develop the extra flux in the opposite direction to the secondary flux, such that they get cancelled itself, and resultant transformer will become constant flux device. So anyway, that will be maintaining only mutual flux. So suppose if the flux produced by the coil will be surrounding only primary side, or if the flux produced by the coil is only surrounding the secondary side, that is called self flux or leakage flux or useless flux. In transformer, it is not required. Our main intention is the flux produced by the first coil must be linked to the secondary coil. That is what we are trying to do here. But it is not happening. Basically, some of the flux will get linked only with the primary, some of the flux will get linked only with the secondary. They are called leakage flux. We are simply calling them as leakage flux. Okay. Similarly, if you observe the rotating machine, it may be any machine. Rotating machines means basically they are having stator and rotor. Yes, sir. So when the moment you are injecting the supply through the stator, flux lines will be produced, or from the rotor. You can take flux lines from anywhere to anywhere. But what will happen is in between stator and the rotor, you will have a minimum air gap. So we will have minimum air gap. Now here the flux which are traveling from stator to rotor, or the flux which are traveling from rotor to stator. It has to travel from stator to either stator to rotor or rotor to stator. That is called mutual flux. They are creating the mutual relation between the stator and the rotor. That is our requirement. If the flux produced by the stator is only rotating in the stator, or if the flux produced by the rotor is only rotating in the rotor, then that is called leakage flux, or that is called self flux. Why it is required for us? First of all, in electrical machines, we are creating the action. Action means that mechanical rotation or electrical power conversion from mechanical energy to electrical energy, whatever it is. Between these two domains, between the stator and the rotor, there is one interlinker. That is called our flux. Without this mutual flux is only the person who is creating the relation between stator and the rotor. So here what will be happening is electrical energy will be converted into magnetic energy, then magnetic energy will be converted into mechanical energy. Similarly, reverse process. In alternator at all, first mechanical energy will be developed, then it will be converted into magnetic energy, then it will goes to electrical energy. So here the intermediary is main flux or mutual flux. Without having this flux, we cannot do any action in machines. So it is very important to keep important to this mutual flux, to give importance to this mutual flux. He is the supreme star. Now the next question is fell in place. So suppose initially what we saw, I was passing current through the only first coil. When the moment you are passing the current through the first coil alone, it will directly create some mutual inductance to the secondary coil. Now, if you inject the current through the secondary coil, it will create some mutual inductance to the primary coil. Okay, sir. So, totally, what is the effect? If you observe, because of the first coil, one mutual inductance will be developed in the secondary coil. Now, because of the second coil, one mutual inductance will be developed in the first coil. And then here the inductance will be L1, here the inductance will be L2. Now, if you observe, the self-inductance offered by the coil is only the first coil self-inductance is simply L1, the second coil self-inductance is simply L2. But if you observe the mutual inductance, always, whenever we are dealing with the mutual inductance, because of the first coil, one mutual inductance will be developed. Because of the second coil, one mutual inductance will be developed. Approximately in our network analysis, this value is always equal. Mutual inductance offered by the mutual inductance offered by, see, let me call like this. So first I am putting 1 to 2 mutual inductance offered by the primary coil, right? This is the mutual inductance offered by the primary coil in the secondary coil. Because of the primary coil, some mutual inductance will be developed here. It will be equal to mutual inductance developed in the secondary coil due to, sorry, primary coil due to secondary coil. You can take like this. So M12 means interlinking between 1 to 2. M21 means interlinking between 2 to 1. So this is the mutual inductance that is developed from 1 to 2. This is 2 to 1. This will always be equal. We can keep the same value. Identically, I am telling. So then what is the relation between this self-inductance and the mutual inductance? That relations will be brought by our coefficient of coupling. Basically, I told you coefficient of coupling will be defined as in terms of flux. I have defined this value, right? So it is see how I have defined it here. Mutual flux divided by total flux. Yes or no? So similarly, this can be defined as mutual inductance divided by total inductance. But it should be under square root L1 into L2. Derivation is there, you might have gone through these things in the lecture. This is in terms of electrical inductance. So from this I can see, sir, this is came from derivation. I have skipped that part here, it is not required because we are in revision session. I cannot prove everything. So it will be k times of L1 into L2. Suppose it is given that coils are identical to each other. Identical in the sense the value of L1, sorry, identical in the sense value of L1 and L2 both are L, same value, that is called identical. In that case, mutual inductance M will become simply K into square root of L power 2 square root get cancelled, it will become K into L. Simply we can say coefficient of coupling will be mutual inductance divided by self inductance. Suppose this case will be true when the value of what I can say, when the coils are identical to each other. Okay, don't forget. Okay, sir. The next question is fall in place with the dot convention. So basically, when the moment we are passing the coil through one coil, sorry, when the moment we are passing the current through one coil, definitely sometimes they will oppose each other, sometimes they will aid each other. It means what? Matlab, 1 minute. When the moment I am injecting the current through this coil, what it will do is it will create some flux. This coil flux will be rotating like this. It will be rotating like this. Similarly, when the moment you are passing the current here, this will be creating some flux like this, creating some flux like this. It will be rotating like this. Now the question is, because of this, see, if you observe in both cases, I am passing the current from lower to, sorry, bottom to top, right? It is going from low level to high level. In both cases, the direction of the current will be remain same. When the moment you are passing the current through the two coils in the same direction, what will happen? The resultant flux produced by them will attract each other, will be attracting each other. So what will happen is the first coil will try to pull the secondary coil. It will pull close to the first coil. Similarly, if you are passing the current through the secondary coil, it will try to attract the flux produced by the first coil. So flux lines will getting, not coils. Physical appearance will not affected, but the magnetic flux lines will get attracted by each other. So in resultant, a single line will be formed there. So if you observe in resultant, you cannot see the whole line. They will be started circulating like this, north pole to south pole. So attraction will be happening. So this is this coil will attract this one, this coil will attract this one. So this is called attraction force. So whenever we are passing the current in the same direction, the magnetic flux created by these two coils will tries to attract each other. So in resultant, a complete attractive line will be existing between them. Sir, suppose if I will reverse the direction of the current in any one of these coil, what will happen? They will repel each other. They will repel each other. Sir, I know I am not proving everything here. And you also know this is revision class. Here everything I can't teach. Just to go on like listen to our lectures. Okay. Just have a recapture once. Fine, sir. So they will be attracting each other. These when the moment you are trying to pass the current in the opposite direction, they are repelling each other. So this attracting and repelling. Basically, I am talking about this attraction and repelling nature about whom. So this attraction and repulse basically is related to the flux lines. But I am just asking you, can you see the flux? No, sir. These flux lines are invisible. Then how can you see this? No, it is not possible. No? Yes, sir, it is not possible. So, as an observer, suppose if you are learning basic electrical engineering, today only you are appearing to the magnetic flux line classes. Suddenly I'm talking about flux, mutual inductance, mutual coupling, blah 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 blah. What you guys will do? Arey, what are you doing here? I don't understand anything, first of all. These things will appear, will come or not? Yes, of course. Immediately I'm talking about go on to bring on transformer which is producing a thousand or 1 lakh magnetic lines. What you will do? You will simply say, I don't know, because this is my first class. So basically, anyone has to understand when the moment they are appearing to the electrical engineering, when the moment they are trying to understand the beauty of this magnetic flux lines, they must know what type of attraction is happening between the magnetic coupled circuits. Like the flux produced by the first coil is opposing the second coil or attracting the secondary coil. In order to know that, you have to see the flux. If I will give the coil, if I am simply giving the coil and asking you, I will just pass the current like this and I will keep one more coil here physically. You are standing here. I'm just asking you. Tell me now what will happen whether they are opposing each other and are aiding each other. What will you say? You won't say anything. Sir, I don't know. Why you don't know? Just tell me. Sir, I don't know why. Because the magnetic flux lines produced by the first coil is invisible. Is it visible here? No, it is not visible. Then how would we know that? In order to clarify this issue, people started evolving this magnetic coupled circuit with one more person, that is called dot coupling. You might have seen many of the magnetic coupling circuit, many questions also. They started putting the dot everywhere. So what is the point of putting this dot? Now, if you observe the circuit from outside, so you can simply identify what will happen when the moment you are injecting the current between the coil. I am passing the current here. In both cases, I am injecting the current in this direction, or you are injecting the current in the opposite direction. You can simply stand here and say something. What I can say, previously you might not guess what would have happened, but now you will be able to say that, sir, whether they are opposing each other or not opposing each other. How will you do that? Let's see. So basically what people will do is, as a manufacturer, when the moment they are first manufacturing the coil, that time itself they will keep everything here. They will keep dot notation for the coil. First of all, I am telling you, see, just now I have told you, if I will pass the current in the same direction, like see there, I am injecting the current from left to right, and here also I am injecting the current from left to right. Now what will happen? Just now I have been told you, now when the moment you are injecting the current in the same direction, in resultant, the net flux produced by the coil 1 and the coil 2 will be attracting each other. So here also what will happen is, only the flux produced by the first coil, let me take self-inductance will be L1, self-inductance will be L2, mutual inductance from L1 to L2, let me call it as M. Again, from this to this, let me call one more M. So totally, what is the total mutual inductance? Because of the 1 to 2 and 2 to 2, 2 to 1, we have mutual inductance effect is always doubling. You might have observed, see, the value of mutual inductance always multiplied by a factor of 2. The actual reason behind of this one is, there are two mutual inductance. Actually, this can be written as M12 plus M21, but basically those two values will be always equal. The mutual inductance created by the first coil in the secondary coil. Similarly, the mutual inductance created in the primary coil due to secondary coil will always be same. So I can call it as twice. Mutual inductance effect is always doubled. But whether they are opposing each other or not. So that can be easily identified with the help of dot coupling. So when the direction of the current will be same, basically they will be attracting each other. So what will happen is, this can be represented. Now, just now we have understood that just by looking into the coil, we can't guess anything because the flux lines are invisible. In order to show that concept properly, they have started evolving the circuit with the help of dot couplings. So let me remove all the currents here. So see, if I will keep the dot, suppose here if I will keep the dot, it means what will happen is, see, in both cases, at the dot, if current is entering in both cases, it means the flux produced by those two coils are attracting each other. That is the first conclusion, attracting each other. In some cases what might happen is, while observing the coil simply from outside, you might be thinking that, sir, in both cases currents are entering in this way, but internally that coil might be reversed, the direction of the coil might be reversed, that might be coming from somewhere. You might have observed these kind of things in DC machine. See, what I am telling is, you'll be simply thinking that, sir, here one coil is there and here one more coil is there. In both cases, current is going from left to right like that. But you might not observe from where that coil is originated. That coil might be twisted from here. The actual direction might be different. So in that cases at all, you cannot simply guess just by seeing the entrance point of it. By seeing the entrance, sir, in both the cases current is going from left to right. That current might be coming from right to left for some coil. You might not observe that. These things they won't give in the examination. That's why just by keeping the current direction also you cannot guess. So we have started evaluating the circuit with help of dot couplings. Now after keeping the dot, if you see in the first case at the dot current is entering, in the second case also at the dot current is entering. See there, here also current is entering, here also current is entering. Opposite side current is leaving, here also current is leaving where dot is not there. So in these type of cases what might happen is the resultant mutual flux will be positive, because the flux produced by the first coil and the flux produced by the second coil will be attracting each other. When they are attracting, then mutual inductance will be positive, 2 times of m, I can say like this. Suppose if they are not attracting each other, so second case they might have give like this. They might taken the same magnetic coupled circuit. Now while keeping the dot, see, let me keep the dot here and let me keep the dot here, no issues. I'm keeping in the dot, I kept the dot at the same position. But when the moment I am injecting the current, I am injecting the current here and I am injecting the current here. Now tell me, flux produced by these two coils will oppose each other or not? Obviously, sir. See there. Here at the current entering point, we kept the dot. Whereas here, current entering means what? Whether the current is entering the inductor or leaving the inductor. See there, here current is entering the coil, then it is slowly rotating, then it will came to the exit point, exit point of the inductor. When it is leaving, it is observing the dot coupling here. It means, see, here at the entrance of the inductor, current is entering, it is trying to entering into the coil. At the entrance itself, we kept the dot. Here at the exit, we kept the dot. So if the dots are in the opposite place, so here at the entrance, we kept the dot. Here at the exit, we kept the dot. Current exit point. This is current entrance point. So both will oppose each other. In this case, the resultant mutual inductance will be in negative value. So because the flux lines are opposing each other, so it will be minus. So I can call self-inductance will be again L1 and L2 only, but mutual inductance will be doubling effect will be there, but it will be minus 2 times of M. Now, if you calculate the total inductance, then what is the total inductance offered by the first coil? So the total inductance can be considered as self-inductance L1 plus self-inductance L2 plus 2 times of mutual inductance. Why I am putting plus here? Because in the first case they are attracting each other, whereas here in the second case, if you observe, I am putting self-inductance L1, self-inductance L2, but mutual inductance will be opposing each other, so I am putting minus. That will be the total inductance offered by the circuit. So I hope you all are observing this. So now see, in both cases at the entrance, if I kept the coil. Suppose I am giving one more circuit now. This is one coil. This is one more coil. Now here I kept the dot and here I kept the dot. But the injected current will be here. Current is at the current entrance, there is no dot. See that in both cases, at the exit, we kept the dot. At the current exit point, we kept the dot. What will happen? See, once again, they won't oppose each other. They will be attracting each other. Why, sir? Why? Because here also current, dot kept at the exit point. Here also dot kept at the exit point. So dot will be placed at the same position. அப்ப நீங்க செக் பண்ணி பார்க்கணும் இண்டக்டரோட current exit pointல டாட் இருக்கா இல்ல என்ட்ரன்ஸ்ல இருக்கா. In both coil if the current is if the dot is placed at the entrance of the current, in both coil if the dot is placed at the entrance like this, or in both coil if dot is placed at the exit, in both of these cases the mutual inductance produced by the coil will be positive only. They will attract each other basically. So the mutual inductance once again will become twice of M only, and the overall inductance will become L1 plus L2 plus M. Why I am putting plus here? Because they are attracting each other. In the same way, this is one coil, this is one coil. Now what I am going to do is, I am keeping the opposite relation. See, in the last case what I kept here, current direction is reversed, right? Now let me do one thing. I will keep the dot here, and I will keep the dot here. What I am going to do is, I am going to keep the current here. See, now I am injecting the current here. I am injecting the current here. Tell me whether these two people will oppose each other or not. Sir, current is entering into the coil. So at the entrance we kept the dot. Whereas here current is leaving from the coil. So at the exit we kept the coil dot. So this is entrance, this is exit. Whether they are opposing each other or not, I told you when the dots are opposing each other. One dot is placed at the entrance, another dot is placed at the exit. Definitely resultant mutual flux will be negative. So minus 2M. Immediately you can write the overall mutual inductance will be L1 plus, sorry, overall inductance will be L1 plus L2 minus 2 times of N. In the same relation for parallel circuits, for that I have to write the derivation, and I'm not going to do that. So kindly do the same analysis for parallel circuit. But that one is not the matter here. You might understand how to observe the difference between these coils. That is very important. Okay, sir, fine. Now, I'm just asking you a question here. Let us take one coil here, and it is connected in series with one more coil, and it is connected in series with one more coil, and it is connected in series with one more coil. This is your examination question. And they have connected one more inductance also. Here, let me keep one more inductor. Like that, they have connected so many inductors in series. Then what they did is, they had given some value like this. This is 2 Henry, this is 1 Henry, this is 3 Henry, this is 2 Henry, this is 1 Henry, this is 3 Henry. So like that they had given the values. After that what they kept is, they kept the dots here. One dot is here, another one dot is here, another one dot is here, another one dot is here, and then they kept one more dot here, and they kept the dots like this. Dots also given. Then they have given certain relation like this. They told this is 1 Henry. Then they have given the relation between these two coil. They told this value is 2 Henry. Then they had given the relation between these two coil. They kept this is 1 Henry, and they had given the relation between this coil and this coil, and they told this is also 1 Henry. After giving all the data, what they asked is simply they kept this is called a terminal A, this is called a terminal B. They asked us to calculate the value of total inductance offered by the network from the point LAB. Sir, how do I figure out that? This is very simple, yeah. How do I do it? What is very simple, sir? First of all, suppose in the examination, after giving this kind of circuit, you must observe carefully if the flux linking line, you can observe this kind of yellow lines is not given between some coils. See, between this coil and this coil, is there any mutual inductance? No, it will be zero. Why, sir? They haven't given. They haven't given. So when there will be no lines, if they have not given this kind of lines, if there will be no this kind of line, you have to understand that mutual inductance between that coil is 0. That is the meaning of that. So you have to consider the mutual inductance only which are highlighted by them. So you don't need to be bothered in this kind of circuit. Mutual inductance will be clearly given by them. They will give you everything. You don't need to be bothered about it. Okay, so you can consider only the given values. So now what you have to do is step number 1. In order to write the total value, listen, break it into two parts. One is write sum of all self-inductance values, sum of self-inductance, one case, and then plus write sum of all mutual inductance value, sum of, see here I am putting 2 plus or minus sum of mutual inductance value. We know it will be doubled always. Mutual inductance value is always doubled, and you must also take care of the sign of the mutual inductance. You will be getting the answer. See, sum of the mutual inductance. What is this? First one is having 2 Henry, second one is having 1 Henry, then 3 Henry, then 2 Henry, again 1 Henry, 3 Henry. So we have added all self-inductance value. Yes, sir. Now it is very important to see. First, I am putting plus outside commonly. Doubling effect. Mutual inductance will be always doubled. I have seen. See, we saw this. Observe here. Mutual inductance will always be doubled. I hope every one of you keeping smile in your face. It is very important. Serious are don't think that we are learning something new. Be serious, be serious. அப்படின்னு சொல்லி மூளையை சீரியஸ் ஆகிடாதீங்க. இட் வில் பி திங்கிங் ஓகே சம்திங் ஏதோ ரொம்ப ஹார்டாக நடந்துட்டு இருக்குன்னு நினைச்சா அது எதையுமே ஒழுங்காக கற்றுக்காது. ஏன்னா அது கஷ்டன்ற ஃபீல் அது ஆட்டோமேட்டிக்காக ஃபீல் ஆகிடும். ஸோ ஜஸ்ட் ஹாவ் அ relaxed mind. Okay, so this is self inductance. Now how will you do the mutual inductance? Let us see. Mutual inductance first given at this point, so this is the first one. Then let me take this is the second one. Let us estimate this is third one, this is fourth one. Totally 4 mutual inductance are given. Let us keep our attention with the first one. In the first one, if you observe, see, they asked us to calculate the value of mutual inductance from L, A and B. From there, just to understand the mutual inductance relation, I am injecting a current. Just inject the current. Do the same way and observe the direction of the current. This current is going like this. Yes, and it is going like this. Yes, so this is the direction of the current. It will be keep on going, it will be keep on, then again you can collect the current at the entrance. Fine, sir. Now observe this. First I am taking the first mutual inductance coil, this one. I am just observing whether these two dots are opposing each other or not. See there, here at the current exit point, only focus at this coil. At the current exit we kept the dot, and here also at the exit point we kept the dot. So both will attract each other. So plus mutual inductance value is what? Only 2 Henry. Yes. Similarly, observe the second one, this one. See there, current is at the entrance of the current we kept the coil. This is at the entrance because this is coil entrance. Now this current is keep on going, and here also at the entrance only we kept the coil once again. So the value of mutual inductance is 1, but it is plus 1. You know the reason, because current is entering into both the entrance. Okay, fine. Entrance dot kept at the entrance of the current. Okay, sir. Now let us keep our attention to the third one. We know, see, for this coil, dot kept at the entrance. We already know that. But if you observe this coil, see there, dot kept at the exit of the coil. So definitely they will oppose each other. Then put -1. Then they have given one more. See, for the first coil at the entrance of the current, they kept the dot. And here at the exit, they kept the dot. See, their entrance and exit will oppose each other. Then I am keeping -1 once again. So what can be the resultant answer? 2 plus 1, 3, 3 plus 3, 6, 6 plus 3, 9, 9 plus 3, 12, plus 2 into, in bracket, -1 plus 1 will get cancelled, plus 2 minus 1 will give you only 1. So the overall value is 12 plus 2 will become 14 Henry. Is there any difficulty in solving this kind of questions? That is very easy, and you know in your examination this model is repeated model. You can observe in many exams, and it is not a difficult question to solve. It is very easy. Just follow the same way that I did here. If you do like that, you will be coming up with the perfect answers. Okay, I hope now you have understand the complete basics of magnetic coupling circuits. Fine, sir. Now let me keep some questions here for your understanding, such that you will get the complete idea about this coefficient of coupling circuits. Remaining things will be covering at last, not here, but I will be dealing with the in transformer. We need to do some questions. There I will be covering rest of all things. Okay, and before that, that the transformer T equivalent circuit, you might understand that one also. Let me keep that on here. This is the representation of transformer with the core. Okay, sir. See, basically transformer is magnetically coupled circuit. We all know this is magnetically coupled circuit, MCC, magnetically coupled circuit. So in transformer, basically there is no interlinking between electrical linking is not possible practically. But theoretically, it has been. We have done some changes and we brought the relations. Why we are here? What is our work? ஏதாச்சும் ஒன்று பண்ண முடியல அப்படின்னா அதை உட்காந்து பண்ணணும். இது மேக்னெட்டிக்லி கப்பலிங்காக இருக்கா, என்னால் இந்த சர்க்யூட் அனலைஸ் பண்ணவே முடியல. ஸோ ஐ வாஸ் திங்கிங், நோ, ஐ ஹாவ் டு டூ சம்திங். வாட் ஷுட் ஐ டூ? ஐ cannot analyze this circuit directly because I'm thinking that I understood that this part is separate, this part is separate. Simply in between them only flux lines are flowing. That flux lines are invisible. What should I do? I need some physical interruption. I need some interpretation, physical interpretation, some physical relation between them. What should I do? People started doing the research continuously on it. Then finally they found a beautiful way. With the configuration, we can redraw this transformer in T structure. You know, ABCD, capital letter T. T will be represented in this format. 1 minute. So if you write the capital T, it will be like this. Correct, no? How will you write the capital T? Like this. See there? It is in the same structure. So somehow they have found some relation between. See there. Now they brought the relation between self-inductance and the mutual inductance. This is called a mutual inductance. This is called a total self-inductance at the primary side. So this is called a total self-inductance at the secondary side. So I'm putting self-inductance at the primary, self-inductance at the secondary, overall value. So they have beautifully explored this from the transformer. How it would have happened? Because we have the dot coupling, they did lot of research, finally they found this. But how do I calculate, sir? So let us see. This is self-inductance L1, this is self-inductance L2. Mutual inductance between them is M. So the mutual inductance between these two people is M. Now it is very important to know whether these two people are opposing them each other or they are aiding each other. How do I know that? In order to know that, we must know the direction of the current. See, let us see. Suppose if I will keep the dot here and I am keeping the dot here and the direction of the current is given like this. Now you should understand this. In both of these cases, observe. Let me take the first coil. Where is the dot? Now write the relation. Sir, for the first coil, dot is appearing at the current entrance. Yes or no? See, this is the current entering point. Current just entering into the coil. Here also, sir, here also dot kept at the entrance only. What we know in both cases, dot kept at the entrance point of the current. In resultant, we can say in that case, the mutual inductance offered by these two coils will be aiding each other. We can keep plus M. So its correspondent equivalent value. So here in that case, at the center of the core, this center coil will be representing only mutual inductance. But you have to identify whether it is positive mutual inductance or negative mutual inductance. So this is the equivalent mutual inductance. It will be positive mutual inductance. Directly, whatever the value that they have given here, you can take and keep it here. then what is the value of total self-inductance offered by the coil at the primary side? So in that case, what you must do is you should take the difference between self-inductance of the primary coil minus mutual inductance. This is derivation. Derivation is there. I am not writing here. I am just writing the relation. Similarly, self-inductance offered by the total self-inductance offered by the secondary coil, that should be equal to self-inductance minus mutual inductance. That's all. So this is how we are evaluating the overall electrical equivalent circuit of the transformer in T format when they are attracting each other. So this attracting case might be in the opposite direction also. See, let me show you. I am removing the dots here. Suppose if I will keep the dot here and here, tell me now what will happen. Since see, current once again current is placed, sorry, dot is placed at the exit point of the current. Here also dot is placed at the exit point of the current. So what will happen? Sir, both are, see, both are exit only. When both are exit, once again the resultant will be, relation will be attracting each other only. Suppose in, now let us go to the next case. In one case they kept the dot not here. If the dot is appearing here, then what will happen? See there, now we must focus one side at the current entrance we kept the coil dot, in another side at the current exit point we kept the coil dot. This case is called, at what I can say, rippling each other. In resultant, the magnetic flux produced by these two coils will be opposing each other. When they are opposing each other, how do I draw the network? Nothing will happen. Just go to the previous circuit. Take the same circuit. Wherever you have the mutual inductance, replace M by minus M. That's all. In all relation. So what will happen? I can draw the same network. There is nothing is wrong here. Here you will have minus mutual inductance because they are opposing each other. And here, see there, self-inductance, I told you in place of M, I asked you to replace minus M. Then what will happen? Already one more minus is there. Minus into minus will become plus. So the value of self-inductance at the primary, the value of self-inductance at the secondary. Let me write. The value of self-inductance at the primary side will become L1 minus, sorry, L1 plus mutual inductance. Similarly, the value of self-inductance at the secondary will become self-inductance at the secondary side plus mutual inductance. Why I am putting plus? Because these two people are, so this is derivation. Okay, don't forget. This is a simple derivation, but I haven't written here. Just to remember. But without keeping these things in your mind, it is very difficult to draw the equivalent circuit. But this portion is very important. That's why I kept my attention here. Okay, just do remember that is very, very important actually. Okay, sir. Fine. So this is how we are drawing the electrical equivalent circuit of the transformer. So I have given the sufficient data. How do I, how to draw these things and how to bring the answers. Now let us go ahead with some of the previous questions that I already told you that. Let me solve those questions, and with that we will wind up the magnetic coupled circuit. So first of all, they told is there are two coupled coils connected in series have an equivalent inductance of. See, they told two coupled coil connected in series. Two coils, two coupled coils are connected in series, and they told that they are having the mutual inductance of. They are telling that they are having two possibilities. Either it is 16 millihenry or it is 8 millihenry. They told. So depending upon their connection, they told that this value, it can be 16 or 8 depending upon their connection. It is depending upon their connection. It is depending upon their connection. It is depending upon their connection. Is it finished? Of course. Now the question is, then what is the value of mutual inductance M? Apply your common sense. We have seen everything, concepts which are related to all magnetic coupling circuit, important things. Now you can take 2 minutes, 2 to 3 minutes also you can take. Try to drop the answer. What is the mutual inductance value for this question? Do it fast. Anyone? What is the answer? Do it fast. Geeta. 2. Very good. Any other answer? Any other? Gauri Muthu, 2 millihenry, Rajesh Khanna, good. Sadhana, good. Sukumari. It's good to hear, and every one of you are answering, right? So 2 millihenry, good. So check my Batalama. Let me also, because I also don't know the answer. But let me try. First, let me read the question. Two coupled coil connected in series. In the sense, they told that there are two inductive coils. They are connecting these two coils in series. So they will be connected in series like this. After that, we don't know basically where is the dot connection. Either the dot kept by them might be opposing each other or attracting each other. So I don't know exact location of the dot. So for that only they have given one more clue. One is 16 millihenry, another one is 8 millihenry. When the moment we are injecting the current through this coil, if I will pass some current, that current will be going like this. Yes, sir. Under this situation, I can't give assurity in how the way they are giving they are creating the relation between them. So either they might be attracting each other or they might be repelling each other. Suppose you know anyway the L equivalent can be written in two possible way. First one is L1 plus L2 plus 2 times of mutual inductance. Sorry, 2 times. Another one is this L equivalent can be written as L1 plus L2 minus 2 times of mutual inductance. Yes or no? Now definitely I can say here we are it is in subtraction, here it is in addition. So that 16 millihenry must be for the first one because all are in addition. So that value must be larger than the secondary one. Second one is having only 8 millihenry. That is the next question. So depending on the connection, they only told that. Now what they asked us, they asked us to calculate the value of mutual inductance M. So let us see what should we do in that case. We can solve these two cases. L1 plus L2. Now in both cases I am just treating L1 plus L2 together, L1 plus L2 together. I am just subtracting the first equation and second equation. If I'll subtract them, then what will happen? L1 plus 2 minus L1 plus 2, they get cancelled. If I'll subtract these two will get cancelled. What about this one? 2 millihenry minus of minus 2 millihenry will become 4 millihenry will be equal to, I am subtracting here also. 16 minus 8 will become 8 millihenry. See, this side millihenry will not come. Sorry, I'm having only coefficient, right? For m. So m is going to be, if I'll cancel it, I'm getting 2 millihenry. Good. So the correct answer is going to be what? 2 millihenry. Once you know the value of mutual inductance, once again you can resubstitute that value here. Now you can again resolve the equation in order to know the value of L1 and L2. You might be thinking, see, what will happen is we found the value of mutual inductance is 2 millihenry. So the first equation will become L1 plus L2 plus 2 times of 2 millihenry will give you 4 millihenry will be equal to 16 millihenry. So from this expression we can say L1 plus L2, what is the value? 4 millihenry. 16 minus 4 will give you the value of, sorry, 12 millihenry. You can also calculate this value with the help of second equation. There what will you obtain? L1 plus L2 will be equal to, see, if I replace this m by 2, it will be minus, if you pass to the right side, same, again you will be coming up with the same 12 millihenry. So it is very easy to identify the value of L1 and L2 together. One more point is together. You cannot easily break them, because to explore these two values, some other clue might have given, but they haven't given that, so that is not possible here. So but I can say the overall self-inductance value is 12 millihenry and the value of mutual inductance is 2 millihenry. Now what is the coefficient of coupling? We know. Is it possible to calculate the value of coefficient of coupling? No sir, the data is insufficient. Why it is insufficient? Sir, to know the value of coefficient of coupling, I must know m divided by square root of L1 into L2. But what happened here? You might have observed this expression carefully. In this case, we have L1 plus S2, but we don't have L1 into L2. So that is not possible. If they would have asked this question, that is, in that case, answer might be what? Insufficient data, sir. We cannot break the value of L1 into L2. Okay, sir. Let us go ahead with the next question. There is one more beautiful question. See, what they did is they have given the transformer equivalent circuit. It is given like this. And they kept the dot also clearly. Sorry guys. So what they did is, 1 minute. So they kept the one dot here and they kept one more dot here. Now what happened is, primary side they are injecting the current here, secondary side they are injecting the current here. Okay. Next they are calling it as, this is inductance L1, this is inductance L2. So this is the given data. After giving this, they have given some names. Let us say this is port A and B. This is port C and D. That is port terminal names. So terminal A, B, terminal C. After giving this, they are evaluating the equal inductance between C and D. So first they are trying to calculate the equivalent inductance between C and D. They are getting 4 Henry, but during that time they are telling that AB is short circuited. I haven't told, they are only telling this. They are telling that AB is short circuited. This is one case. Again, they are evaluating the value of inductance across the same terminal. So, sorry guys, 1 minute. This is open circuited first case. So first case is open circuited. Second case, once again they are calculating the value of LCD across the same inductance. Second case they are getting 3 Henry, not millihenry, 3 Henry when AB is short circuited. Now it is short circuited. Primary is short circuited. This is the given. Now the question is, then calculate the coefficient of coupling. You can take 3 to 4 minutes for this. I am giving my time. So just to try to evaluate the circuit. It is clearly given that, I am repeating one more time, it is clearly given that A, B, C, D, there are 4 terminals for the 2-port network. Out of that, they are short circuiting the AB and open circuiting the AB. During the process, they are trying to calculate the total equivalent inductance across CD. So they are obtaining something. and that value is clearly given, that equivalent inductance first case is 4 Henry, second case is 3 Henry. With these clues, kindly estimate the value of K. First of all, whenever you are facing the transformer circuits, what you have to do? What is the step number one? Can anyone please tell me? What is the step number one? Before doing all these things, first identify the dots positions, whether they are opposing each other or attracting each other. So based on the nature of them, you know how to draw the transformer equivalent circuit. Just now I have shown the physical interpretation between primary and secondary. We have drawn the electrical equivalent circuit for the superstar transformer. It's very beautiful, we brought the relation between them, and we also saw how to bring the that interpretation between the primary and the secondary in terms of mutual inductance, and whether it is positive or negative, everything we have defined. Just go ahead with this data. Try to step number one, whenever this type of circuit is given, draw its electrical equivalent circuit before evaluating this circuit. After that, you can proceed further. You know how to calculate the inductance for series and parallel configuration. You can proceed with that. Do it fast and bring out the answer. Got the answer? Anyone? If you found the answer, just drop it in the comment section. Got the answer? Just think and try to bring the answer. Fine. Let me try to bring the answer. For some question, patience is very important. You have to observe the question. See, listen, once you understand the basic, the question that are being asked in examination directly, definitely it will come from the basic only. But they will keep some tricks in each and every question, right? That is very important. Without tricks, then it will not be a game. It will be boring for us. So let us play with this given circuit. Actually, what they told is they got four entry Gita one. Very good. Let's see. They got four entry when the terminal A and B is short circuited. First of all, let me draw its electrical equivalent circuit. You all know how to draw the electrical equivalent circuit of the transformer. Just now I taught you. So when the moment we are trying to estimate, let us see first. Okay, so this is the electrical equivalent circuit, but I don't know where to put minus, where to put plus. For that I'm going back and I'm observing. See, if you observe the secondary loop, current is, sorry, dot kept at the exit point of the current, first one. If you observe the primary side, dot kept at the entrance point of the current. So entrance and exit both will oppose each other. First conclusion. Opposing in the sense, here we must keep minus and here we have to keep L plus M and here we have to keep L2 minus M. You know how to do this. Finish. Now after that, since remaining are same, so this is a terminal A and this is a terminal B, this is terminal C and this is terminal D. There is no doubts. Now what they are telling, they are giving the first clue. They kept the AB as open circuited. See, what is the meaning of open circuit? Can anyone please tell me? What is the meaning of open circuit? Sir, if any one terminal is open circuited, in the sense you must apply the ideal condition for that impedance offered by that network will be approaching to infinity, open circuit. When the impedance will be approaching infinity, that open circuited terminal, immediately if I am trying to explore the current, I is equal to V by Z. When impedance is approaching to infinity, I can write V upon infinity or it will be equal to 0 ampere. So it is clearly indicates that the current flow through the open circuited terminal will be always 0. You might be thinking, sir, how it is possible practically? I know it is not possible practically. You are doing everything on the paper only. Under the transformer circuit also not practically possible. We have drawn the electrical equivalent circuit. This could be only possible on a sheet. So that's why I am applying it. What is wrong with that? Practically this value should be very, 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 very high. So it should be in the order of 10 power 12. Automatically current will become nanoampere. So it will be 0, even picoampere also. Fine, sir. Nanoampere means what? 10 power minus 9, almost 0.80 you have to keep. So it will be 0 only, na? Approximately current always be 0 in open circuited terminal. So now, according to case number 1, so according to case number 1, the current entering into the primary side will become 0 because they are open circuiting it. That is the clue. Now tell me, is there anything will happen in this circuit now, in this inductance L1 plus M, primary side inductance? Nothing will happen, sir, because current experienced by that coil will become 0 ampere. Now it became useless. Under this situation, if you estimated the value of mutual inductance, sorry, total inductance from here, not LAB, sorry guys, that is CD. If you estimate the value of inductance across C and D, what you might obtain? See that now if I will inject any current here from the secondary side, that current will go here, it will go here. Then after reaching this junction, it may tries to go through this coil, but it is not possible. It will be 0. Why it is 0? We know the reason. We know the reason why current will not flow through this line. So the injected current will get diverted through this coil. It will go through this one. Again, it will be coming back to the same point. It clearly tells us that what it's clearly, sorry, this is L2 plus M. It is clearly tells us that these L2 plus M and this minus M both are connected in series when the primary is open circuited. So I can add all the value L2 plus M and minus M. This is the overall inductance. So minus M plus M is getting cancelled here. So I can say the value of LCD equal to simply secondary coil self-inductance L2. Do you remember the value of LCD is already given, that is 4 Henry when primary is open circuited. So if I will substitute here from this, we concluded that the value of L2 is approaching to 4 Henry. Yes or no? Yes, sir. Now, let me take the same circuit one more time. Let us do the analysis with the second given data. They had given one more data. See, just observe the way that I am observing. I am doing the analysis. I know the basic, right? I am just applying the basic. I don't know. I am not teaching anything new and I am not doing anything new. Whatever I taught you, I am just applying it. So here, once again, it is L1 plus M. This is L2 plus M. This is minus M. So they have given the terminals name already. So they are calling it as, this is A, this is B. They are calling it as terminal C, terminal D. Next, in the first case, they have open circuited the A and B. Now they told that they are short circuiting this. It means this terminal will be short circuited with this. Yes, sir. When they are short circuiting the terminal, what will happen? Nothing will happen. Now, if you observe, suppose if I will inject any current from the secondary coil, if I trace its path, this current will go, will go, will go. After reaching this junction, definitely some of the current will be flowing through this line, some of the current will be flowing through this line. So it is clearly indicate that current will be splitted into two parts. So you can call this current is Ix and we can call this current is Iy. But it clearly indicate that whenever while passing the current, you know why we are injecting the current here, in order to know the series parallel configuration. I don't know which inductors are connected in series, what are the inductors are connected in parallel. In order to know that relation clearly, I am just injecting the current, and I also taught you this is the best effective way to identify the series parallel configuration relation. So here I clearly understood that this inductor and this minus M both are connected in, see, this L1 plus M and this minus M both will be in parallel because current will be divided. So now first estimate the parallel equivalent. So for this, you know how to calculate the equivalent value, L equivalent parallel configuration. For this we can write L1 plus M. This one is connected in parallel with the minus M divided by total inductance L1 plus M minus M. This is addition of total inductance. In the denominator, if you observe, minus M plus M got cancelled. So here for this parallel circuit, I am getting L1 plus M into minus M. In the denominator, we are having L1. This is the overall value. Now, if I am keeping that resultant circuit, see there, I am reducing that parallel configuration. In resultant, we have calculated that parallel equivalent value. I am substituting that value directly here. What we got here? L1 plus M into minus M upon, I think, L1. So here it is L2 plus M. Already we have estimated this value. And this is the terminal C and this is the terminal D. Now if you observe the circuit once again, I am looking for LCD under this situation. What is this? This coil and this coil both are connected in series. So the overall equivalent value LCD will become equal to L2 plus M. It will be connected in series with, I can write like this. I am interchanging the position, minus M into L1 plus M upon L1. So I hope you all have understood what I am trying to conclude here. Now let us open up the brackets and we will try to reduce the circuit. L2 plus M minus M into L1 minus M into M will become M square upon L1. So again, we can further simplify this network. So L2 plus M1 is given here already. Sorry guys, someone. Okay. Now let us reduce this. L2 plus M. Can I write like this, minus M into L1 upon L1 minus m power 2 upon L1. Can we write like this? See there, L1 getting cancelled here. Now if I will further simplify it, this L2 plus m minus m minus m power 2 upon L1 minus m plus m will be cancelling. That's why I am asking you to go to the final step, till the final step. What some of us will do is, after writing this, if we might have doing wrong, we don't get the answer. That negative thought will automatically appearing in your mind and you will be skipping the steps. Don't do like that. While solving the problem, you don't know till the final end whether you are doing correct or not. Do it till the final point. If you don't get the answer at last, that time you can think whether you are doing correct or not. You don't judge in this off first of itself or starting itself or writing the two or three step itself. Don't guess that you are don't estimate yourself that you are we are doing wrong. We don't get the answer. Don't do like that. Okay, that is wrong approach. Okay, sir. Let us see what will happen. LCD. Finally, we will be coming up with L2 minus m power 2 upon L1. I think LCD is already given, right, for the short circuit. See, when the moment you are short circuiting the AB, the overall LCD value is already given as 3 Henry. So let us substitute this value is 3. It will be equal to, we can say L2 minus m power 2 upon L1. Yes or no? It is or no? So from here, they told that L2 is already we know, right? So we found the value of L2. 1 minute. Where is that? C. Here, the value of L2 equal to 4 Henry. It is already given. So let us substitute that value. So it will be 4 Henry minus m power 2 upon L1. I hope you all have understand this. 1 minute, guys. Okay. Now from here, if you observe, 3 minus 4 will be equal to minus m square by L1. So minus minus will be, see, 3 minus 4 will be minus 1, so it will be 1 equal to, I can say it will be m power 2 upon L1. So from this I can say we found the relation between m square and L1. Yes, sir, we found the relation between m square and L1. Now, let us estimate the value of coefficient of coupling. K is equal to, we know the basic formula. It will be m upon square root of L1 and L2. Yes, sir. So, this will be m upon square root of L2 value we know, that is L1 value is just now we saw, that is m square into what is value of L2? L2 I think 4, no? L2 is 4 only, yes. Now see there, you can take both outside. 4 upon square root of m square will be coming out of m. So if you take 4 outside, it will be 2. So it will be equal to m will be cancelled 1 by 2. So it will be equal to 0 0.5. That is the question, no? The value of coefficient of coupling is dash. That is the question. So finally, we found the value of coefficient of coupling is equal to 0. This value is equal to 0 0.5. See how beautifully we got the answer for this question. It's a really beautiful question. They have not given anything. They have just estimated the value of equivalent inductance. See in this question, mutual inductance is not there, self-inductance is not there. But sir, we have estimated the value. That's the beauty of question. See, I haven't done anything. Remember one more thing. This coefficient of coupling K, ideally it is 0, but practically this value should be greater than 0 and it should be less than 1. Do remember this. This is for practical case. But ideally the value of K equal to 0, coefficient of coupling. Why I am writing this point here? You should apply your common sense for this. See, what I told you that K is the coefficient of coupling simply. And here we are writing that is the relation between mutual flux upon total flux. Now tell me, Mutual flux is simply one or two lines which is going to be connected with the another part of the coil. Whereas the total flux value is what? Total flux offered by the coil, pi t. So this phi t value is always greater than the value of phi m or not. This is very important. When the denominator is greater than the numerator, then the overall value should be less than 1 or not. So it should be less than 1. Okay, so don't forget this concept. They are very important. But ideally it should be what? When I am approaching, sorry, 1 minute, let me tell you. Ideally K value should not be 0. It will be equal to 1. Because what is the case? Why we are intentionally designing this coupling circuits is it has to link with the primary. If I am injecting some if I am passing some flux through this line, it should be totally linked with this coil. But when it is not linking completely, the value of coefficient will be 0. When it is completely linked, see, in the question, if they will given 100% coupling, if the circuit is given as 100% coupling, then the coefficient of coupling will be 1. Why? 100% coupling in the sense total flux will be linking with the secondary coil. Pi m will be equal. So do remember this way. Don't remember that ideal case at all, because it might be confusing you. Anyway, in the examination, they will be talking about percentage only. So if they will give 100% coupling, it will be K equal to 1. If they will give you 50% coupling, K equal to 0.5. In 2020-22, now in the bark examination, they did the same way. What they did is they have given the value of this coefficient of coupling in percentage. 50% of the flux is linking with the secondary coil out of total. It means what? Key is given as 50% of the flux linked with the other coils out of total flux. It means they are basically talking about coefficient of coupling 0.5. Bark exam recently conducted, no? So that is the answer. They have not answer. It is one of the key that was given in that question. Same way, they have given the clue for L1 and L2. Question is we have to find out the value of mutual inductance. But the value of K is not given. Instead of that, they have given the definition. Part of mutual flux, 50% of the flux is linked with the secondary coil from the total flux, out of total flux. So such that from that we can easily identify the value of K. So the value of K equal to 0.5. Now you can calculate the mutual inductance. M is equal to 0.5 into square root of L1 into L2. If you put, you will get the answer. So it is very important to observe this. So it will be different in terms of percentage only. Do remember this relation hereafter. Okay. Okay, let me give a few more questions for you. I brought here. See, here, what they clearly told is 1 minute, guys. Sorry for the disturbance. Now here, let me write. Number of turns N1 is given. They told that number of turns N1 is 20, and then they told N2 and N3 both are equal number of turns. So they told that the number of turns are 10. Now find the current I1. The question is find the value of I1 equal to dash, whereas the value of I2 is given. The value of I2 equal to 10 ampere at an angle of 53.13 degree. So this is given and it is minus, don't forget, minus 53 points. So this is minus 53.13 degree. Then I3 also given, that is 10 at an angle of minus 45 degree. So the value of I2 is given and the value of I3 is given. Everything is given and a dot coupling also given. Now it is your responsibility to bring the answer. You know the relation between circuits, dot coupling also, everything we saw. Just evaluate the value of current I1, I2, I3. Okay. Sorry, only I1. I2, I3 is already given in the question. You don't need to do anything with that. Okay. So we have covered almost all basics that are required in magnetic coupled circuit. See, here this is simply revision class. I may not be able to bring everything here, but what is my responsibility? To bring something which you might not observe everywhere. நம்ம படிக்கும்போது ஒரு சில விஷயங்களை ப்ராப்பரா அப்சர்வ் பண்ணியிருக்க மாட்டோம். I am covering everything here. And I know from which area questions will be majorly taken. I'm also covering those areas. But I may left some portions in all other chapters also. It is your responsibility to complete those things also. Even in lectures also, I have been told many times, if you found something new in problems, something may be missed in the lecture, immediately don't wait for anyone. Use all multiple resources which are available in this platform. We are in digital world, everything is available here. Simply in your mobile itself, you can bring everything. Don't be lazy. So try to learn. If something is missing in the lecture, if something you are learning new, or something if you want to practice, immediately go to Google, search everything. There are so many Android apps are there, YouTube is there, Google is there, textbook is there, practice question books are there, hard copy, soft copy, everything is available. Try to utilize maximum all the available resources. That is the way you should work hard. That is called hard work. Basically we are calling it smart work. Okay, but I told you that don't use that word is called hard work. Just enjoy the game. Just love the studyings. Do try to love the subject, try to love the concept. Just create the enthusiasm. When you're learning something new, you have to create some curiosity into your mind. Wow, it's really beautiful. That's all. So that is how you have to learn. Okay, fine. So we have completed electrical circuit theory fully, network analysis almost. So if I left something, it is your responsibility to cover those also. And one more thing, try to solve as many problems as possible. That only will help you to understand the subject, to enhance your problem solving ability. But don't forget to keep clock with you. That is very important. I have told you always while solving the problem, don't spend more than 3 minutes in any question. Try to solve as speed as possible. If you don't know the concept, blindly skip that question. If you know the concept, try to bring the answer. But don't spend too many times. See, listen, in any exam, the exams that you are looking for, except IES, in the entrance exam, they won't take any question which will consume more than 3 minutes. So question might consume 1 minute or less than 1 minute. Some questions may go to 2 minutes. It's too difficult to find some question which will take more than 2 minutes. But I'm giving rare chance you people are in practice zone. So it is better to go up to 3 minutes. But still, if you are going beyond 3 minutes, you are not in the right path. Either you should increase your speed or the way you are solving the problem might be wrong. So just observe those things. They are very important. Okay. So this is all for this lecture. Remaining things we will see in the next class. Thank you all.